Hello, I am Brandon Fortes, and I am a computer science major at Louisiana Tech University.
My name is Ariana Schwab, and I am a mechatronics engineering technology student at Penn West, California. We spent the summer at West Virginia University studying legged localization in forested environments. Firstly, localization is the act of a robot estimating its position in an environment. To do this, a robot will use various proprioceptive and exteroceptive sensors to determine where it is in its environment. Algorithms then take information from these sensors and fuse this information together to allow the robot to have a rough estimate of where it is.
Forested environments add several more roadblocks to the localization challenge. Factors such as inconsistent lighting, plants and wildlife, seasons, precipitation, and varied terrain all impact localization negatively. Notably, these problems make exteroceptive sensors far more inconsistent than usual, so a robot in this environment must be capable of localizing itself with proprioception alone. Our goals with this project were to test various localization solutions in different scenarios, identify the sources of error in each test, and document these sources to gain a better understanding of how they impact localization. Additionally, we aimed to implement improvements to the algorithms to account for these errors. To accomplish these goals, we had a unitary go-to robot walk around on various different surfaces and terrain while estimating its position. We got estimates from two different odometry algorithms, a purely proprioceptive solution called go-to odometry from NVIDIA Paris Robotics, and an IMU and LIDAR-based solution that is built into the go-to robot. These estimates were then graphed against a motion capture ground truth.
Here we have a video of one of our tests. All of our tests were conducted in the Vicon Lab, a facility with a motion capture system that we used for the robot's ground truth position. In each of these tests, the robot walked in a specific path on a specific terrain, in this case, a circular path on rubber. Estimates from the odometry algorithms, as well as the raw sensor data, were recorded for each test such that future analysis could be done. The graph displayed shows the data captured from the various sensors on the robot and the data from the Vicon system. The blue line is the ground truth, the orange line is the proprioceptive odometry, and the green line is the built-in odometry.
This is another one of our tests, this time walking on an M-shaped path on slippery terrain. As you can probably tell, the slippery terrain made the robot's movements much more unstable, which had major impact on the resulting estimates. As you can see in this graph, the localization estimates were far more inaccurate than in the other test. Due to the robot not traveling as far as it expected with each step due to slippage, the algorithms drastically overestimate the distance the robot traveled.
We also recorded and graphed some of the raw sensor data to observe the behavior of the various sensors. For example, we used this foot pressure sensor graph to diagnose issues with the individual sensors and adjust their tuning in the code accordingly. Additionally, saving recordings of the data allowed us to recalculate the odometry estimates for each test as much as we wanted.
Root mean square error was the metric used to evaluate the accuracy of purely proprioceptive solution in each test. This graph shows the RMSE for each several of our tests. As expected, estimation accuracy degraded significantly on slick surfaces. Additionally, longer paths like the circle and long S-turn tests were slightly less accurate overall, as purely proprioceptive solutions degrade in accuracy over time.
In the future, we want to attempt to improve the go-to odometry algorithm to make it more accurate, set up simulation software to conduct more tests, improve upon the feet of the robot so the robot can grip the floor better, and look into using SLAM as another means of localization.
We would like to thank our sponsors, NSF, for funding this project, as well as our faculty mentors for guiding us through our research.